So now we have an experimental perspective, I guess. So when you're ready, Dan.
Okay, well, thanks so much. It's a pleasure to be at a real conference in person. It's been such a long time, and back at Rice, I was actually an undergrad here and have wonderful memories. So it's always great to be back. So thank you. Okay, so I'm Dan Dessau. Is there a pointer? Just this probably does not show up on Zoom, I guess. And minimally there. Excuse me. Doesn't even show up in real life. Okay, anyway, I don't need to point much here. I'm Dan Dessau. I'm from the University of Colorado Boulder. And I'm going to tell you about some of our electronic structure measurements of magnetic topological materials. Thank you. Oh, that's much better. All right. Okay, so topology and magnetism. It's a really nice combination. Our community, of course, is quite familiar these days with topology that brings, for example, surface direct cones. But with magnetism, we break the time reversal symmetry that is one of the important protectors of many of these topological states. So by bringing magnetism in, we can exert control of the topology and the topological interactions, occasionally, for example, by gapping these Dirac cones by breaking the topological, by breaking the time reversal symmetry. And a great example of this was this beautiful paper out of Chin-Ka She's group, where they observed the quantum anomalous Hall effect in these chromium-doped bismuth telluride films. The chromium here are the magnetic impurities. On the other hand, this effect is limited to 30 millikelvin. And it's believed that this disorder, the magnetic disorder from these doped impurity states, is really what limits this. So this particular sub-branch of the field, for example, is moving to ordered magnetic topological materials with much less magnetic disorder. I'll be talking about these materials in part one of my talk, in particular the manganese bismuth tellurium family. In these, the quantum anomalous Hall effect has been observed at higher temperatures, Kelvin scale, but it's still much lower temperature scale than we envision might be possible based upon the quite large exchange fields. Okay, so that'll be part one of my talk. Part two, I'm going to talk about another very interesting magnetic material. We're calling this CuMNAS, or copper manganese arsenic. It's an antiferromagnet. Back in 2016, Pete Wadley and collaborators showed that they could electrically switch this by running current, electric current, in one of two directions and observing a perpendicular resistance in multiple directions. And you can see the change in resistance as they pulse in the different directions. So the effect works, but this is at present a quite small effect. It's due to what we call AMR, or anisotropic magnetoresistance. The goal of my talk is to use topology. Well, the future goal is to use topology to turn this into something like an order unity effect. We're not there yet, but I'll tell you progress along the way and understanding along the way. So that's part two of the talk. Okay, so in these Mn bismuth telluride compounds, the main compound that people have really been working on is the 124 material. It's an intrinsic ordered magnetic topological insulator. The nail temperature is of order 4 Kelvin. So again, it brings magnetism and topology together. The field was really launched by Otrikov. And here is a picture of the crystal structure and some ARPAS data from their paper. Okay, so this material has septuple layers, 7 individual layers with the manganese at the center, That's in contrast to standard bismuth telluride, which is quadruple layers. There's 5 layers in a typical bismuth selenide or bismuth telluride. So here we have 2 extra layers, septuple with the magnetic manganese element in between. From their paper, they're arguing this is the surface Dirac cone here, and it's gapped with, you can see a quite large energy scale, many tens of millivolts approaching 100 millivolts. So very large exchange field of the claim. So this really set off the field. The quantum anomalous Hall effect was then observed in odd layer sheets. So particular 5 sheets of septuple layers. Temperatures up to 1.4 K with no field or 6.5 K with a magnetic field because the material likes to be antiferromagnetic. So this flips it to become ferromagnetic. But still, these temperatures are much, much lower than the exchange energies that claim are probably gapping the Dirac points. So why must temperature scales still be so low? Well, one argument is related to magnetic disorder that the community is now believing might exist at the surface. And the first evidence of this came from another ARPES paper on the same material. And here you can see, they see a beautiful surface Dirac cone that is ungapped. So basically same material, and there's controversy about this. Is it gapped or is it gapless? And something my group is working hard on right now to really try to understand, to deconvolve the surface states from the bulk states, observe all changes with temperature. I would say it's complicated. And definitely things are not as beautiful as you might imagine. And I'm not going to really talk about that, partly because it is complicated. Okay, but we do believe there is magnetic disorder at the surface. What I'm going to tell you about is a new set of materials where we can bury this top magnetic layer a little bit below the surface and maintain some of the magnetic order. Okay, and these in particular are heterostructures of this magnetic 1,2,4 compound, the septuple layers with quintuple layers of the bismuth 2 tellurium 3. And these materials are grown by my collaborator Nini from UCLA. Extremely fortunate to have this collaboration with her and her group. She's a real wizard in being able to grow the many, many different heterostructures in bulk form stably. They have very narrow windows of stability between them. And so we're extremely fortunate. Anyway, this picture you already saw. We call this one 147. There's alternating 124 and 023 layer. Call this the 023. There is 1610, which is one magnetic layer with 2 1023 layers. This is the 1813, et cetera. It goes on and on. And one important thing to note is that this compound, these individual magnetic layers are ferromagnetically aligned between them, whereas here they're antiferromagnetically aligned. Each layer is ferromagnetic in plane, but then antiferromagnetically aligned out of plane for all of these other ones. Okay. So we have these materials. We were fortunate enough to get them and to start doing ARPES on them. One of the difficulties is that the cleaves can occur anywhere within a stack. And there's a possibility to expose one of these quintuple layers as well as a surface layer. It's a difficulty and it's also a benefit. Okay, and that's as shown here. For these bulk crystals, when we cleave them, we actually get, for example, for the case of the 1813, we get 4 possible surfaces that are maybe extremely close to each other. And so one of the challenges for us was selecting what each different surface is, delineating them, understanding each of the many different surfaces. We succeeded in that, and I'm going to show you different Fermi surfaces we get for the different compounds. So these are the 4 different terminations that are possible up to 1813. For the 1610, there's 3 different possible terminations. There's 2 terminations for the 147, et cetera, and only 1 termination for the 124. And you can see there's various Fermi surfaces, okay? Initially, it wasn't obvious which was which, but by comparing to following all the trends, comparing to theory, et cetera, it soon became pretty clear. Let me now show you what the E versus K spectra look like. Again, for the 3 compounds and the 4 possible surfaces. And now you can really start to see trends. So for example, and let me just say this is all along gamma to M direction. So gamma is at the center and then out M in both directions. Gamma to X looks similar. Okay, and I'm pointing out what you might call the charge neutrality point, or where the Dirac cone would live. There is a gapless peak here, gapless state, evolving to things that look more and more gapped as we move down and as we especially go to the QL1 surface. In other words, the surface with 1 non-magnetic layer at the top, and we argue that one is still ordered, whereas when there's just the SL surface, we don't have a gapped state. And we argue that is due to the magnetic disorder there. We can take this data, which I already showed you. Now I'm just focusing on the 1813 compared to DFT calculations, as shown here for the different surface terminations. And the agreement is, I would say, satisfactory. It's good. It's certainly not perfect. But similar dispersions, very similar structures, as you can see, including this largest gap for the QL1 surface. Okay, now what does theory say about, well, shows the gap, but what's really behind it? Well, it shows that really the hybridization between this top SL, let's see, between the buried SL layer, the magnetic layer, and the top QL or non-magnetic layer, that's really a major component of the gapping. Okay, because we are looking at surface states. We'd like to see magnetic gaps in these topological surface states, but the magnetism is a little buried, but at least it is robust. And so here's K.P model showing the Dirac surface-like states from the QL with an SL state going between. And we turn on magnetism, and then we turn on some hybridization between them. And now you can start seeing these magnetic gaps at the surface. So where does this leave us? Well, we would argue that for the future, a beautiful place to be would be to create thin films of this 1813 compound. And this is the ferromagnetic compound. And if we could fully terminate at the QL1 surface, for example, with layer by layer MBE growth, and put the chemical potential here, then this would be a beautiful place to be for high temperature quantum anomalous Hall type physics. Okay. I'll move to the second half. How am I doing on time? 5 minutes talking. Okay, thank you. Okay, so this is moving to the second set of materials, this electrically switchable antiferromagnet, copper manganese arsenic. And this is collaboration with Pete Wadley's group from Nottingham and Smeckel and Youngworth from the Czech Republic. Okay, so again, Kumnos, it's this room temperature antiferromagnet. The magnetic elements are these are the manganese. And they have a special arrangement. They're symmetric spatially, but they're anti-symmetric according to the spin. And so there's a PT symmetry, and due to the spin-orbit coupling, the electric currents are able to rotate the nail vector. And so that's what's happening here. As they're sending the current either this direction or this direction, they're rotating the nail antiferromagnet direction from this way to this way, okay? And it's reversal. They've done quite a bit of work on this. They claim the switching happens at terahertz speeds, et cetera. It should be achievable with very low spatial dimension because of very low fringing fields from the antiferromagnetic order, et cetera. The problem, as I mentioned earlier, is this is a very small effect at present. The hope would be to bring topology in, to use different nail vector orientations to open gaps, open Dirac gaps due to the magnetism, okay? And then have something like an order unity effect rather than the very small effect from the AMR, okay? So what we want to do is we want to find these Dirac points. We want to see if the electron structure calculations that predict them are reasonable. So we were successful at doing ARPEs on these MBE grown films. Of course, we need a clean surface that was obtained by protecting them with an arsenic top cap, which we're able to then remove in vacuum. There's some details that are not really important to us here. There are some weak surface reconstructions that you can see in the lead, but in general, the lead pictures show the very high quality of the clean surface, and ARPEs works well. And so here's just a few shots. These are experimental Fermi surfaces at different KZ values and with different polarizations that's overlaid with DFT as shown here. And the agreement is quite good. One thing to note is to get this agreement, we had to do two things. We added a U value and we worked quite hard to determine the best possible value. It's just near 2 EV. And we found that we needed to hole dope the Fermi surface by something close to 400 millivolts. And with that, we get an agreement both in the Fermi surfaces and in the band dispersions, which is the next page. So experimental data with the DFT calculation shown in red. Here's the DFT in more detail now with band orbital symmetries shown in. And those symmetries we've shown also match exactly the ARPEs using polarization analysis. Here's an overview, again, of the DFT plus U calculations. States are primarily manganese. Our chemical potential is down here. This is the roughly 400 millivolt shift, unintentional doped shift. And I would say the initial sad thing is we moved away from the Dirac point, which is the one we really wish to control. This is the Dirac point. Theory says different magnetic orientations should open a gap, for example, along X direction versus along Y direction and give us control for the switching. But we know where we are. We know what we wish to do, and that is to sort of move back towards and then even beyond. And so that would be the next step for us. If we can do that, then the claims we should be able to get unity level switching as we change the nail vector. So switching of the order of 1 versus this is something like 2%, which is where the field is at present. Okay, so that is my last real slide. Summary again, using topology plus magnetism gives us a mechanism for exerting control of the electron topology through breaking of time reversal symmetry. Can bring new materials and device functionality with these two examples. Okay, thank you for your attention.
Okay, questions? Silke?
Yes.
I should say it would be great if students and other younger people can ask questions too.
Hi, thank you for the great talk. So is it fair to say that you are actually controlling magnetism and topology follows Would you agree to that statement?
Well, for example, if you're opening or closing various gaps, various, direct points, gaps through the magnetism, we're okay. I think I agree with you. It's sort of it's a mixture. The effect of the topology and the magnetism together is what we're controlling.
But your control is on the magnetism, right?
Yes.
Okay.
Yes. Yeah.
But the control of magnetism is because the material has topology, so that you can run current.
And because the topology is there, sure, that has nothing to do with topology. So here, that's the time reversal symmetry is, for example, protecting that anti-crossing. That's the direct point. You break that symmetry, and now the anti-crossing, if you like, is enabled.
Then the very nice talk. Can I ask how big of a gap you expect to open in this copper manganese arsenic?
In this compound. Yeah. Okay, so you can read it off from here. It's in this one particular case, it's small. This is 200 millivolts, so that's 10 millivolts scale, something like that, which is still somewhat sizable. The material in antiferromagnet at room temperature, I don't expect we would find, a room temperature gap though.
So then, do people know what the size of the spin gap is in the system?
That's never been observed.
So so basically, it's not quite sure how the current is modifying the spin gap, because the spin gap reason.
So the present observation is the AMR, because chemical potential is far away from any of these points, which we finally know.
Okay, so then
Yes.
very nice talk.
Yes.
So second part, so here after switching, why does not go back?
So it's a thing of domains. It's domain physics.
45-degree
So
domain
there
physics.
can be antiferromagnetic domains aligned in one direction. You can switch them. They can be other. You have to overcome all these domain energetics.
But there's 45-degree domains, not 90-degree domains. It's a 45.
These are 90. These should be 90-degree domains.
Oh,
This should
90-degree
be the most.
So high temperature is
favored.
a tetragonal. High temperature is a tetragonal, and then just domains.
Yes, this compound is tetragonal.
Oh, I see. Okay, it makes sense. Now go the first part. This may be a long story, but I heard some discussion about possible different magnetism near the surface.
Yes.
And also magnetic domain walls may contribute to this zero gap mode. Can you kind of tell us briefly what is happening?
I am calling it disorder at this time, and domain walls with tiny enough islands, sure. On the other hand, what we really believe, each layer, though, we believe those when it's away from the surface, is ferromagnetic, and that energy scale is relatively large.
But still,
But at the surface, then the disorder is much more severe. And then, yeah, are there domain walls or whatnot? I'm sure there must be.
This is a very simple question. You carry out full emission because I cap it with arsenide, right?
Yes.
Will arsenide capping with arsenide self-dope it?
Okay, good question. So we tried different decapping procedures, different temperatures, etc., going very hot, try to remove any remaining arsenic. Basically, that makes almost no difference in the chemical potential where we land. You might imagine a little bit on, or you went so hot you removed arsenic that's inside. Seems to not be the case.
So from what
Yes.
you're saying, these different layers, does that mean that the controversy over whether the surface of manganese bismuth telluride is gapped or gapless, do you think that's no longer a controversy? It could be entirely explained by which surface people were looking at?
So let me say the main controversy in gapped versus ungapped is on the 1,2,4 compound, and there's only
Not the one here.
one type of surface
Got it.
on that.
Okay.
There is still controversy whether it's gapped or not. What I would say from the two slides I showed you, I think the real case is somewhere in between. I think there are gaps to the surface states, but they're definitely not as big as we would like. And the temperature dependence as you go across this nail temperature is also not what you would really like to see. So we'll be putting out a sort of detailed thing, but it's not as fun as you would like.
Still a minute or two more, if anybody else wants to ask something. Otherwise, we can make up a little bit of time, I guess. No? Okay. So